Welcome to the Disk and Washer Method Day 2. So we're going to continue our discussion on how to find volume of three-dimensional objects by finding first a area and rotating it 360 degrees around an axis of rotation. Today we're going to focus on rotating around axes other than the X and Y axes. So we're going to actually rotate around other lines of rotation. So for example, we'll find the volume of the solid formed by the region bounded by y equals the square root of x, y equals 0, and x equals 4. Let's begin first by identifying x equals 4. I've already plotted it up there. It's a vertical line. And that's what I'm going to rotate around. I'm going to take whatever I plot here, I'm going to rotate it 360 degrees around this axis here. So imagine that is the thing, or the hinge, that I'm going to swing it around. So now we have to plot this thing. So first, I'm going to bound it with y equals the square root of x. And of course, if I plot this, the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. And that's basically good enough for now. I know that this function does continue past those x values, and those positive x values, but that's one of the first boundaries. The second boundary is y equals 0. So that's, of course, the x-axis. And finally, the last boundary is, again, that x equals 4, which is already plotted. So the area that I'm going to rotate is right in here, bounded by those three lines. And I'm going to take that blue little wafer, or I don't know what you want to call that, and rotate it around that axis. So it's going to look kind of like the base of a mic stand, like we did yesterday. It's going to look something like this when we're done, where that's the top. It has sort of the circular base, right? And you've rotated that cross-sectional area around 360 degrees to make this three-dimensional shape. All right? You can almost think of it as if you cut the top of the sphere off. All right? So what I need to do now is think about where my rectangles are going to be. Are they going to be vertical or horizontal? Well, they should be horizontal because I'm starting at this axis of rotation and measuring it this way, right? And that's the disk I'm going to rotate around 360 degrees. There's not going to be a washer here because there's no hole. The area that I'm rotating meets up with the axis of rotation. So since I'm using horizontal rectangles, it should be a delta y. So I'm going to be integrating with respect to y. So that means that these equations, or these function values, the height or radius of that rectangle is going to be whatever the function value is of this green boundary. But the green boundary has to be in terms of x equals. So that's a pretty easy solution. All I have to do is square both sides of this. And now I have y squared equals x. And that is the function I'm going to integrate with respect to y. Now the disk method says that I need to take pi times the integral. In the balance of integration, I'm looking at y values. I'm going to start here at the bottom at the lower y value. Again, I don't start here because the y value is 2 and this y value is 0. So I'm going to integrate from the y value of 0, the x-axis, to the y value of 2, which is the top of that green boundary. And the radius is going to be determined by that green boundary here. But you might be tempted just to throw y squared in there. However, you're measuring from the line x equals 4. So that's actually kind of my top of the radius here. So if I wanted to measure this distance here, I'd start at 4, and I would subtract whatever x squared was, because that's how far away the rectangle is going to be from that edge. I know it's going to take a little while for it to sink in, but I want you really to think about if I want to measure heights of rectangles. The height of the rectangle is between 4 and wherever this green line is. And to measure the distance, it's 4 minus that. So that is going to be my radius. My radius of the disk will be 4 minus this y squared here. Hopefully that makes sense to you. If you want to think about it another way, this is 4 minus the x value, wherever the x value is, right? 4 minus whatever x value it is, but x is y squared. So it's pi times the radius squared times the height, which is the dy, the little tiny width here, the delta y. So I need to integrate that. It's going to be much easier to integrate if you just distribute it out by binomial expansion, and then use the general power rule, use the fundamental calculus to evaluate the integral for its bounds. You see we get an approximate volume of 53.617 units cubed. And again, that's going to be the area of this rotated around. All right. right. Now we have to rotate a solid bounded by y equals 4x minus x squared and y equals 0 around the line y equals 5. So you can see here that my axis of rotation is horizontal now. I'm going to rotate around this horizontal line here. So, but I have to make my boundaries first. 4 minus x squared, well, 4 minus x squared will look something like this. 4 minus negative 2 squared would be 4 minus 4, that's 0. 4 minus negative 1 squared is, 3. 4 minus 0 squared is 4. 4 minus 1 squared is 3. 4 minus 2 squared is 4. And there's my first line. And of course it goes farther down than this. But it's a parabola opening downwards with vertex at 0, 4. And the other line that's bounding it is y equals 0. That's the x-axis. And you can see that I've trapped in a little two-dimensional area that I'm going to use a highlighter to color in. So here it is right there. It's kind of a little, I don't know what kind of shape you'd call that, like the tip of a rocket ship or something. There it is. I need to rotate that whole shape 360 degrees around that line. And so you can imagine what that might look like. It'd be reflected up here. And if you kind of connect the dots visually, there's going to be some hole in the middle, but it's going to be kind of a strange shape here. So this is actually a washer method problem. So the washer method with a horizontal axis of rotation is the integral from a to b of the outer radius r of x squared minus the inner radius, lowercase r of x squared, with respect to the variable x. And so we need to determine what is the outer radius of my washer. And we're going to start using this function down the bottom, not my go shape on top. So capital R of x, what's the farthest edge from the axis of rotation? If you drew a rectangle up and down like this, what's the farthest end from this axis? I'll draw a couple rectangles to get you sort of acquainted here. How far is this bottom always? It's a fixed distance away, isn't it? Well, that outer radius is always going to be 5. It's 5 units away from the red line. So R of x, capital R of x, would be 5. Now the lowercase r of x is really sort of tricky to think about. I'm going to try to go slowly through this to help it sink in. If you think about how far the distance from the red line is to the blue line, you start at 5 and you just subtract the boundary line. So for instance, if I wanted this distance right here, I would take 5 minus whatever the blue value is, and then I get that purple line. If I wanted this purple line for the lower boundary of the rectangle here, it'd be 5 minus whatever that value is. So lowercase r of x is 5 minus the function 4 minus x squared. So if I plug that in, here is the setup. Now I did some simplifying here. 5 minus 4, if I distribute the negative to both of those, it'd be plus x squared, then being 1 plus x squared. And so now you should be able to find the volume of that thing rotated around. And I just don't really have time to do that right now. Just kidding, I had time to do it. Here it is. It's a lot of math, but you can just follow it step by step, line by line. You see my simplifying, you see my integrating, you see me doing the definite integral here, forgot a bracket there. Do some simplifying of fractions and using my calculator to simplify there. Thanks for watching. Have a good night. Make sure to watch the summary.